Hi, welcome back to the uncompetitive inhibition derivation. Now we are at part 2. We want to get our equation in this form, where we have V equals to V max into S over K, the Michelin-Menton equation, into S. So these two are supposedly constants with respect to S and V as well. But we want it to look like this so that we can compare the uncompetitive inhibition reaction kinetics to the conventional uninhibited reaction kinetics. So this is the inhibited, this is the uninhibited. We want to have some sort of mathematical comparison. And to do that, we want to make sure we take all these equations and then we make it into this form where we have one Vmax and one Km as constants. Okay, so in the last video, we got to this point where we kind of made the top look quite similar to this top here, and the bottom we have one S term here and one Km term, which we thought was this. However, this isn't really a constant, is it? So to make it a constant, we want to factorize all the S terms to the left hand side on the bottom. So you have this, this S term I'm bringing out of this bracket, and I'm factorizing this and S out of this and this, so that you have 1 plus I over Ki, and then you have a K1 on the right, and the top remains unchanged. Okay, so it's looking a little bit like this now, right? Except you have this lumpy term that's put into like your S term here, which makes it a little difficult to compare. So let's do one more step. We'll divide the top and bottom by this term 1 plus I over Ki, and then you will get something like this: 1 plus I over Ki, and then you will have that into S, and you have a standalone S and K1 over 1 plus I over Ki. There you go, you have something like this, and you have a term Vmax and Km, these two constants, well, which are constant with respect to S and this V. So it's only going to be varying with temperature, because that determines the equilibrium constant, and of course Vmax here, and the inhibitor concentration. So you can see that when you compare this and this, this is obviously going to be lesser than this. So this is Vm apparent, and this is Km apparent. Okay, so this is going to be less than this. So both are going to be reduced. So you have Vm apparent here into S over S plus Km apparent. Alright, so that is more or less our enzyme kinetic derivation for uncompetitive inhibition. But I want to go on to a more special case where you have substrate inhibition. So what is substrate inhibition? Well, okay, let's do our normal Michaelis-Menten equation. You have E plus P. Yeah. So if you have a substrate inhibitor, instead of I, your I becomes this S here. So this is a special case of the uncompetitive inhibition. Okay, a special case of an uncompetitive inhibition. So we have ES2. Okay, so what would the equation look like? Now, since we've already derived our equation here, we'll just substitute S wherever you find this Ki in there. Okay, so let's take this one, which is rather convenient. We'll just substitute S here. So we'll have Vmax and S on top. So the V equals to the Vmax into S over S plus K1 over S squared over Ki. So let's do S plus K, big K1, it's the big K1, plus S squared over Ki. And that is it. We've just gotten our expression for the reaction rate V. Okay, so of course it increases with so this V increases with S up to a certain point, and depending on these two constants, it will start to drop later on. So you have V here, and you have S here, and you'll go something like that. It's a very lovely sketch, but that's the idea you kind of want to get. And of course, what else? Yeah. You notice that we can't do a very similar trick to what we did here. We can't have this, this as a constant, because now all these terms here will start to depend on S. So this will look like standard. This will not look like standard Michaelis-Menten kinetics at all. But well, the reason is kind of because of this, because you have this substrate inhibition. So up to a certain point, you have the so-called maximum reaction rate. And then after a while, it kind of tapers off. And well, you kind of know how to get this maximum rate. You have to do some differentiation. You have to do some differentiation. So you have this dV, ds, and you have the dV ds equals 0, which is at this point. dV ds equals 0, then you have some S max, and you have this Vmax. Okay, and does this Vmax here correspond to this Vmax? Not necessarily. Yeah. Well, you have to perform these calculations and to see whether this whole thing here will become 1 and you'll cancel everything out. I mean, that's the other cheap way of doing it. So okay, let's do it the so-called cheap way. I'm not going to differentiate because differentiating can get messy. But let's just equate 1 to this and see whether it works. Sorry, S squared over 2Ki. Okay, so let's move this all to the left-hand side. S K1. Now this is quite a neat experiment. It's not the conventional way to do things, but it certainly seems to work. Okay, so let's move this to the left-hand side. Oh, you don't need to do that. Just cancel these two, because you can subtract S from both sides. Then you have this. And that will equal to 0. So this, again, let's slow down. We multiply everything of this to the left-hand side. We multiply it by this denominator. and we are left with this expression here. So let's subtract both sides by that. Okay. Then we get a very funny, equation where you seem to have imaginary numbers. So looks like you do have to do the differentiation method. Okay. Yeah, we will have to do the differentiation method in order to get our Vmax. And since we can't use the shortcut method, well, let's just try differentiating this equation. And let's start on a new sheet of paper. I'll try to keep this short. Alright. Vmax. Yeah, we want to find the maximum point of that curve. And you show whether it's equal to this, whether the maximum point of this curve will equals this Vmax. So that's the first part. And then we want to do something, we want to divide the top and bottom by S. So this becomes 1 and this becomes this. Over 1k1 over S plus S over ki. So this is the inhibition, this is the first equilibrium. And then we'll differentiate. Ts equals to, alright, so this is to the power of -1, so we'll kind of use the chain rule. So we bring the -1 down. Then we have the Vmax here. Then we reduce the power by 1. So we'll do this. S over ki. So then we multiply by the differential of the inside. So the first is 0. Because you differentiate, 1 is 0. The second is that you will do this differentiation. So -1, 1 over S squared. Alright. Then you times k1. So the last one will be just 1 over ki. Okay, so let's just be quick about this. Over 1 over S plus S over ki holding squared. So minus k 1 over S squared plus 1 over ki. Okay, and then we'll set dVds equals 0 at midpoint or maximum point. Okay, so this thing is definitely not 0, so we can just divide both sides by whatever this is. So we'll divide both sides by this, and we'll have this side remaining, because this cannot ever be 0, because this is a non-zero term, right? The bottom is a non-zero term. It will always be, usually I guess, 1 or more, because this is 0 or more, this is 0 or more. Okay, so yeah, the substrate concentration is usually always more than 0. So this is a positive number, this is also a positive number, so this cannot be 0. So dividing both sides by that is completely legitimate. But this, instead, it can be 0. Okay? So let's move the first term to the left, this term to the right, and pretty soon multiply this, multiply both sides by ki and this S squared, you'll get this equation. K1, ki. And then you'll have S equals the root of ki, k1, and you get a positive root. And that is where your maximum point is. And what if you substitute that back into this V? So, well, let's just try that. 1 K1 plus, the K1 Ki plus, so this is Vmax. K1 Ki over Ki, and that will equal Vmax, the root of K1 Ki. So we'll multiply both the top and bottom by this factor. So K1 Ki plus K1 plus K1 Ki over Ki. So cancel these two out, and then you have this number. K1. I apologize for the mess. Just ignore the bottom. Okay, so you see the Vmax, and you have the square root term here. So now you have 2K1, which is this one, the Vmax, and this two root terms. And I'm going to divide both top and bottom by this square root term. Then you can see what the correlation is like. K1 Ki. Otherwise, you can write it as this, root of K1 over Ki. So this will be the value of Vmax. Okay, so that's probably it for this video. I won't be spending too much time longer. So in this video, we have learned about the non-competitive inhibition and the substrate inhibition. We found out where this Smax was and where this Vmax was. And we know that this Vmax will never reach this Vmax so long as this substrate inhibition, because we just mathematically derived it. Well, if the substrate is inhibiting itself, it will never be as much as when the substrate is not inhibiting itself. So okay, that's all I have for you. See you guys next time. Bye.